okay, in front of you so that you know what they are. I'm going to give you a couple more today. Those are also quite straightforward. Okay, it's not too complicated. But the first one is the combined gas law. The second one, of course, is the ideal gas law. Okay, and then last time we talked also about R. Okay, in there. So applications of gas laws. As I said before also, gases are very interesting and they have applications everywhere. Okay, you may not realize it as such, but they do have applications everywhere. Okay, and so gases are everywhere also. Okay, so it's kind of good to know the properties of gases. And one of the things that you can do with the ideal gas law is you can either find the molar mass of a gas or you can also find the density of a gas. Okay, and then use that to identify an unknown gas maybe. Okay, or if you wanted to calculate the density of a gas, you would be able to do that. So for example, all the densities of gases there for the noble gases, you can calculate that. Okay, so using the ideal gas law, how do we do this? It takes a little rearrangement. It's nothing to worry about, but we have the gas law as PV is equal to nRT. And I'm going to rearrange that equation just a little bit. Okay, so nothing to worry too much here. All the things that we have in there are still the same. It's just that I'm going to put them in such a way where I can rearrange it a little bit. When you calculate density of anything, the units you need are grams per volume, and volume would be liters, okay, or milliliters. Milliliters is what you learned in chapter 1. Okay, grams per mil is what you do. Here for gases, we're going to do grams per liter, okay, because gases occupy so much space. So that's where we are trying to get to. Okay, so density is grams per liter, and molar mass. What is molar mass? What are the units for molar mass? And that's from the periodic table. This can't be hard. Atomic acid. Okay.
Grams per mole.
Grams per mole. Okay, so that's where we're going towards. N here is moles, V here is volume. Okay, so what I've done is I've taken out some of these units over here. These units here, pressure, temperature, and R, these have nothing to do with any of these units here. Okay, so that's what we have tried to do, is to just separate those out. And very honestly, in the long run, this is not going to matter. Okay, because now what I'm going to do is multiply both sides with M, and that is molar mass. How's that? I'll write that down here. Multiply both sides with M, and M is molar mass, okay, which means that I have M, N over V, P, R, T, M, okay, on both sides. We're just trying to get to a different equation, that's all, okay? It's just a little bit of a derivation, okay, and not too much there. So then over here, molar mass is grams per mole, right? And so the moles and the moles get cancelled out. Are you still with me? So if the moles and the moles get cancelled out, you're left with grams over volume, and grams over volume is density, okay, right there. So that's how you come up with an equation that has density and molar mass, okay, in there. So here we are left with grams over volume, P, R, T, M is still here, okay, for that matter. And so then when you can rearrange the equation so you can find density or molar mass, so in this case, we're trying to find molar mass. So molar mass is then density RT over P. Okay, this here is density. And you can rearrange the equation, okay, and calculate for D. So D is going to be MP over RT, so that's density, and this is for molar mass. Okay, so you have two more equations. I will give you either this one or that one, either the first one or the second one in your exam, and then you can rearrange whatever you're calculating for, okay, in there. So these calculations also very, very straightforward. There's nothing to it. So for example, here's a problem. Calculate the density of helium gas in a balloon at 25 degrees Celsius when pressure is equal to 1.10 atmosphere. And as I said before, I love formulas because all you need to do is find the right formula, plug everything in, and you should have your answer. Okay, so since we're calculating density, this will be our formula right here. Okay, so D is MP over RT. Molar mass, M is the molar mass, and so since we're dealing with helium, you find the molar mass of helium from the periodic table, which should be about 4. So 4.00 grams per mole, and if you want to write the grams per mole like this will be fine also. This will be helpful in crossing out the units, okay, eventually. Pressure, 1.10 atmosphere, and all of this is divided by R, which is 0.0821 liters atmosphere mole Kelvin times temperature, and temperature is 25 plus 273, which is 298. If you want to use the 0.15, you're most welcome to. Okay, so 0.15, 0.15. So 298.15. Depending on how many decimal spaces you're working with, it might give you a very small difference in your answer. So moles, atmosphere, Kelvin, and you're left with grams and liters over here, and the density is 0.179 grams per liter. Good, so very straightforward. Okay, there's nothing to it, and let's do another one. Determine the molar mass of a gas with density 5.14 grams per liter at 73.0 degrees Celsius and 1.00 atmosphere. Since we are dealing with molar mass, we can use the first equation. Convert Celsius to Kelvin, so plus 273.15, 0.15 here, 64364 Kelvin. Density is given to us as 5.14 grams per liter. R is 0.0821 liters atmosphere mole Kelvin. Temperature, draw a big line there. Temperature is 346.15 Kelvin, and pressure is 1 atmosphere. So convenient. Liters, atmosphere gone, Kelvin gone, and you're left with grams per mole, which is what you really want for molar mass, okay, of your gas. And that's going to be about 146.
If you come up with a molar mass of a gas, is that a way to find out what gas it is, like on the
You
periodic
can,
table?
yes. No, not on the periodic table necessarily. It depends where you're looking, okay? So if you're looking out in nature somewhere, then yes, probably periodic table. But if you're working in a lab, then maybe you're making a gas, okay? You're synthesizing something. So when you're synthesizing, it may not be on the periodic table, right? It could be a combination of things. So yeah, it depends on what you're doing. Okay, so you use these things to identify gases or just to calculate density, just because you need to have a data point. Okay, anything that is made, anything that is synthesized, you have to have physical properties for it: melting point, boiling point, density, all of those kind of things. Okay, so yeah, that's what these are. Okay. The next application of gas laws is not exactly an application of gas law, but it's one of those gas laws as well, and that is partial pressures. And do you remember the scientist Dalton? Yes, Dalton's atomic theory, okay, from back in chapter 2. Dalton is the one who also worked on this one, okay, over here, partial pressure. So this is actually Dalton's atomic theory. And what Dalton stated is that if you have a mixture of gases, okay, like in the atmosphere right now you have a mixture of gases. If you have a mixture of gases, each of them is going to exert its own pressure. And so the total pressure that you have is actually the pressure coming from each of those gases, okay, not just one gas. It's going to be for every gas, which seems pretty logical right now. So it means that P total is equal to P1, P2, P3, any number of gases that you have in there. Okay? So just as a curiosity question, okay, for you, how many different gases do we have in the atmosphere? Name 5 for me.
Oxygen,
Oxygen.
nitrogen, hydrogen.
Carbon.
There's no hydrogen. CO2.
Carbon dioxide.
Well,
Carbon dioxide.
Carbon dioxide. Okay. All right. Very good. More? Hopefully not too much. This is so high in Florida. This is so high in Florida.
Chlorine.
In the summertime, in
Water?
August. Water vapor. Humidity. Okay, so you have these 5 gases, okay, so oxygen, nitrogen, carbon dioxide, helium, argon, those are very less, okay, in there, and then of course the water vapor, okay, which is the highest proportion gas in atmosphere. Gosh, no, we'll die. You'll die of carbon dioxide poisoning. So which gas is the highest proportion, percent? Of nitrogen. Okay, yeah, not oxygen. Okay, we think that oxygen might be. Oxygen is the element that occupies the highest percent on the whole globe. That is true. Okay, oxygen is an element, like not as an O2, but oxygen as an atom. Okay, not as an atom also, but it's in combined form as well. Whatever it is, you'll find oxygen. That's the maximum. But in the atmosphere, in the gases over here, nitrogen is the maximum. Do you know how much maximum? About 70%, exactly. You know, 70-75% is nitrogen, which means, okay, this law here makes a lot of sense once you know about all these things, because then you realize that the gas that you're breathing in is actually not just oxygen. You're actually breathing in nitrogen, carbon dioxide, helium, argon, all of these gases. Carbon dioxide also you're breathing in. You're not using it, you're exhaling it, okay, eventually. So without using it, you'll exhale it out. Same for nitrogen, okay, you'll exhale that out without using anything. Until we become legumes and start consuming nitrogen, it's not happening, okay? So you just exhale the nitrogen, okay, as it is. So all of these different gases, they actually exert their own pressure, okay, on your lungs. So which means that if you change the proportion of gases that you're breathing in, then your lungs are going to feel a different pressure, okay, coming from the different component of gases, what will change everything, okay, in your system. So you might have heard of hyperbaric systems. I don't know if you've heard of those, hyperbaric treatments, okay, where people actually get treatment with more oxygen, okay, in a chamber. Like almost like a sun tanning, but I think there's a picture in your book also, okay, for it, and you can read about it. And so what they do is they treat people with more oxygen in there, and this is for people who cannot process oxygen or have less hemoglobin, or they're going through cancer radiation therapy, those kind of things, okay? And so therefore they need more oxygen in their system sometimes, and so hyperbaric chambers do that for them, okay? But not everybody is capable of handling that much oxygen, okay? Do we have any divers over here? Divers, only one diver? No, there's no other divers, okay. Not even thought about diving?
Oh,
Yeah, okay, well.
I free dive, but not actually like scuba.
Okay, well, scuba diving is what I'm talking about, because that's when you have to take a tank and go down, okay? And so when you take a tank and you go down underwater, there are two things I would like to address over here. First of all, the tank that you're taking down, Jake, you might be able to tell me that, okay? Is that pure oxygen? I hope not. Okay, because again, it's the same thing. When you're breathing here in an atmosphere, you're breathing a certain pressure of oxygen. And so when you go underwater, you also want to have the same pressure of oxygen. So you have to take the same proportion, okay, as you would have here. You just have compressed gas, okay? That's all it is, but the proportion is different, okay, in there. And the second thing that I want to bring to your attention, and I just want to ask you out of curiosity, okay, and you might be able to do this, and Jake, don't answer this one, is as you're going underwater, okay, as you're going underwater, you know, as you go underwater, the water also exerts pressure on you. What will happen to your lungs as you're going underwater? Will they compress or will they expand? What will happen? They will compress. Compress, everybody compress? Yes, they should, right? Because you're exerting more pressure. So apparently 10 feet of water doubles the pressure on you. Okay, it's like more 10 pounds of pressure on you. So yeah, your lungs are going to compress, which means that when you're coming up, your lungs are going to expand. Okay, and that's why divers are told to come up a little slowly. Okay, and so they don't expand their lungs very fast. Okay, so it's a slow expansion because lungs can burst. It's happened. Okay, and so people don't come up slowly, then they can cause harm. Okay, and so that was Boyle's law, right? Pressure and volume. That's Boyle's law right there. Practical applications. Okay, coming back to partial pressure then. And for here, I have a little worksheet here for you too. So this one also will do a little bit here, and then a little bit you'll do at home. Okay, so here I'm going to do question number 1 for you. And question number 1 here is for partial pressure. Okay, and this worksheet is on partial pressures and stoichiometry. So question number 1, okay, in this one, a sample of air collected at STP contains 0.039 moles, 0.039 moles of nitrogen, 0.010 moles of oxygen, and 0.001 mole of argon. Okay, so you have 3 gases in there. Find the partial pressure of oxygen, okay, in here. And this is at STP, and this is a critical thing, okay, to know also that we're working at STP. Do you remember your conditions? 0 degrees, 1 atmosphere. What's the volume at STP? It's right there. Okay, 22. Yeah, okay, all right. So remember those conditions. Okay, so the question here is, what is the partial pressure of oxygen? So to calculate the partial pressure of oxygen, which should be coming from here, you need to find out the mole fraction of oxygen first, okay, is how much is oxygen out of the total, okay, in there. To find that, you will need to do this, 0.010 moles of oxygen divided by 0.039 plus 0.010 plus 0.001, and that is moles of nitrogen, moles of oxygen, and moles of argon. So you'll have to add all the 3 gases together, find how many moles of oxygen you have in there, okay? So that's kind of finding what is called the mole fraction. Once you know the mole fraction, then we can go ahead and find the pressure. Okay, so I think I have it here somewhere. So this is 0.01 over 0.05. That gives us 0.2 moles of oxygen. And that is a mole fraction of oxygen. Okay? The mole fraction of oxygen is going to exert its pressure. Okay, so you cannot just take the moles of oxygen and find out the pressure. If it was just the moles of oxygen and you find the pressure for that, that would just be like PV is equal to nRT. But that's not what this is. Okay, this is a mixture of gases. So you will have to find out the mole fraction first, how much it is contributing compared to the total. Okay, so that's what you'll do first. So now we have 0.2 moles, and this is not really moles, this is more like a mole fraction, okay, as I wrote over here, of oxygen, okay, and this is not the end yet, okay, because we still have to find the pressure, okay. So what's the pressure at STP? 1 atmosphere, and that's why I was asking you, because the conditions here are stated as 1 atmosphere, okay. So the next thing is to convert this into atmosphere. So 1 mole of gas at STP has 1 atmospheric pressure, so which means that it's 0.2 atmospheres. Okay? Whenever you have STPs, your calculations become a lot easier. Okay? You don't have to think too much about a lot of numbers. Okay, so that's how you would calculate the partial pressure, okay, of one of the gases. So you can do the same for nitrogen and argon and everything, okay? So that's how it works. The second question here is then, what is the volume of the container? Okay. Now again, remember this is at STP. Okay. So volume of the container. For here, what you will need is the total moles because you have a total gas. Okay. So total moles is 0.05 moles. In 1 mole, what's the volume at STP? 22.4. Okay, and so you make life easy for yourself. In 1 mole, you have 22.4 liters of volume. Okay, so keeping those kind of things in mind, your life becomes a lot easier. The other way that you actually use partial pressure, and this is also very common, is when we start collecting gas over water. Okay, and this is something that is completely new for you. You're doing a reaction that produces gases, okay? 1 gas, let's say carbon dioxide, whatever it is, okay? And you want to collect that gas and find out how much it is, okay? So which means that if here's your reaction vessel, then you will need a tube that will collect the gas. This is all stoppered, okay, so that the gas doesn't get out. And then you will have to collect that gas in another flask. Will that work? Will this give you an accurate volume of the gas that is formed? No, because Samara?
Because gas is so far apart, there's empty space.
And so?
So it's not giving you an accurate volume.
Well, that means that I could collect it in a beaker and it would still not give me an accurate volume, right? Okay, that's not exactly the reason I was looking for. Okay, but you're almost on the right track there. So anybody want to pick up on that? Yes, Jacqueline.
Well, you're going to have expanded gas within the apparatus that you're still collecting, like within the neck of your siphon or whatever that is.
Over here?
Yeah.
In the tube? Yes, that's true too. So if you remember from your alum experiment also, nobody got 100% yield, right? So we all got less than that. So that is definitely something to account for, okay? All right, so no problem, we'll account for that also. Will this still give you an accurate volume of what you're trying to do? I'm still not there yet. I'm still waiting for one answer that will tell me that this will not give me the accurate volume. But why? One of the first things that we talked about in gases is that gases will occupy the entire space. solids you can mold into shape, right? Because the molecules are closer. Liquids will occupy the space of the bottle. And if you can lift up your bottle there, Dylan. As the water is being drunk, what's happening there? Okay, I'll do it. There's empty space here, right? Okay. What is here? Air. As Dylan drinks more water, what do you think is going to happen to that space?
Fill with air.
It's going to fill with air, right? And by the way, for a chemist, there is nothing like a half a glass of water. Okay, it's because the glass of water is always full. Okay, it's either with air or with water. But in any case, it's getting filled up with air. So is that an accurate volume of air? No, because air will just fill up any volume, right? So if I put a 250 milliliter glass there, the volume is going to fill up to 250. If I put 125 milliliter, it will fill up 125 milliliter. Do you see what I'm talking about? It will occupy the space. That's what I was hoping for. Okay, that you will answer. Because whatever size of flask I have there, that is the volume I will have. But that's not accurate volume because that doesn't tell me anything. Okay, because I can just change the flask size and then I can get the volume. So obviously something is different here. Okay, and so what I have to do is I have to have a trough of water. So here's water, and I will have to have a grad cylinder over here which has markings on it, and I have to have the tube coming through here, out here, and the gas is going to come through here. So all of this is filled with water. So as the gas is coming out, the bubbles are coming and the water is getting displaced, just like there. Okay? But except that now we are actually making the gas, and so therefore the water starts getting displaced. So by the time your reaction is done, maybe it's displaced only to this much. Okay? Depending on what kind of reaction you're doing. All right? And so now this is an accurate volume. Do we see the point here? Okay. So what did we do here? This is called collecting gas over water. Okay? Because you have to have water in there, you have to have some liquid that will get displaced as the gas is coming out. Okay, so that's what's actually going on here. And this is an important part with partial pressures because, so we're not done yet. Here's my next question. Why do we have to talk about partial pressures when we talk about collecting gas over water? Because you're right, it is not. Okay, you're right, it is not. The pressure over here that you're exerting,
Vapors H2O.
okay, the pressure that is being exerted over the water over here is coming from what? The gas that you're collecting, right? The gas that you're collecting, and what? And what else?
And the gas on the outside? Is the gas and the gas on the outside?
No, there is no outside. This is inside the cylinder, right? This is inside the cylinder. The water. Okay, because you have water, humidity, we were just talking about that. Okay, so if you have a certain temperature, the water vapor is also going to be given off. And so when you have water vapor, so you will always have some sort of pressure from water also. Okay, so the total pressure that you have is that of gas as well as the water vapor, okay, in there. So that's why we have to talk about partial pressures, because now this is not just the pressure of a gas, it's pressure of water as well. And if you look at the last page of this handout that I gave you, there's a table in there, and that table tells you the different pressures of water vapor at different temperatures, because as the temperature increases, the vapor pressure also increases. Okay, as you know, the water will start evaporating more, okay, if you have higher temperature. So here, as the temperature is increasing from 15 to 25, the pressure that is exerted by water is also increasing, okay? Although it's very, very small, right? Compared to the large scale, it's very small. It's like 20, 22, okay? It's very less, but still, okay, it is there. There is something that is being exerted. Are we good? Okay, all right, all of this, okay, for just that, okay, a little bit of water vapor. Okay, that's why we talked about this. So this is a very common thing that we have to do in labs when you're working with gases. Okay, and you want to know how much gas is formed in there. So the pressure that you get from this gas is not an accurate pressure then. Okay, it has the vapor pressure of water. So you have to account for that, which means that what you do is you measure the temperature in the lab at the time of the experiment. You find the vapor pressure of water at that experiment, and then you subtract the two, okay, to find the pressure of gas. So P gas then is equal to P total minus P H2O. Okay, that's how you find the pressure of gas. It will be a very minuscule change, but it is a change. Okay, so if you look at the next question in your worksheet then, question number 2, a sample of hydrogen gas is collected over water at 19 degrees Celsius. What are the partial pressures of hydrogen and water vapor if the total pressure is 756 mmHg? So the pressure can be given to you in mmHg. It's possible that your textbook has the pressure given in torr, okay? Now don't forget, torr and millimeters of mercury, they are completely the same things, right? 760 mmHg is equal to 760 torr also. So you can, completely interchange as you like, no problems. And obviously I have a hard time finding all these tables in the textbook because I don't mark them, but they're here somewhere, okay? And so you can find it here also, but you have a reference in this worksheet as well. 189?
199.
199. Okay, thank you very much. So you have the table there. Is it in torr? Okay, very good. Because sometimes it's in torr, sometimes it's in millimeters Hg. You gotta watch out for the units. Okay. So here the partial pressure of hydrogen and water vapor is total is 756. So P total is 756. Okay, in there. So what is the partial pressure of hydrogen? In that case, you will go back to the table. You will find the vapor pressure of water at 19 degrees Celsius, which is 16. Subtract the two and get the pressure of the gas. Okay, not very hard to do. It's just a little thing to remember. I will never give you a simple question like that, by the way. Okay, in an exam, you know that. Okay, it will never be like this. It will be part of a bigger problem. Okay, and we have to do a stoichiometry question today. We have to, address that. So when we go over that, I'll show you how we actually use it. Okay, but yeah.
So should we memorize like,
No.
the temperature?
No. I don't know how many times I said that. Okay, no, don't do that. All right, yeah. You save your memory cells. I have more stuff coming for you. Okay?
You'll give this.
All right.
Yeah, that'll be on the. This will be on our
Yes, if you need it, I will provide it for you. Okay, so yeah. I mean, I give you the formulas. Why would I have you memorize the table? Okay, it doesn't make any sense. Okay. All right. So, gas stoichiometry, just like any other stoichiometry that we talk about, for stoichiometry you look for a chemical equation, all right, and a chemical equation that should be balanced. You look for mole ratios, okay, in there, and the third thing how you approach is, of course, is how you calculate moles, okay, in there. When we started working in chapter 3, we got our moles from grams. In chapter 4, we got the moles from molarity, okay, and now here we're going to get our moles from PV is equal to nRT, okay, from our ideal gas law. So depending on what kind of a problem is given to you, you decide how you want to approach it, okay. Usually there is not many ways, okay, that you can approach it. There is only one way. So let's go ahead and try a couple problems here. What volume in liters of carbon dioxide can be consumed at STP by 525 grams of sodium dioxide. Na2O2, you've not seen this before. This is an unusual compound. I'll give you the equation. Na2O2 plus carbon dioxide to give sodium carbonate and oxygen. And to balance the equation, we have 2 of Na2O2, 2 of carbon dioxide, 2 of sodium carbonate, and oxygen is fine. Solid, gas, solid, gas. I'm hoping by this time, since we're in chapter 5 now, you're very comfortable with identifying what is a solid, what's a gas, what's aqueous, things like that. Okay, and aqueous is definitely only for chapter 4 though. Okay, those kind of things where you have precipitations or acids and bases. Okay, so what volume in liters can be consumed at STP by 525 grams of sodium dioxide? That's the question. So if this was chapter 3, you would be calculating the grams of carbon dioxide, but this is not chapter 3. Okay, we're in chapter 5 now. So which means that once you take this and you convert it to moles, okay, and then you do the mole ratio, after that, the moles that you get here, you'll have to convert that into liters. Okay, so how do we do that? Is by the gas laws. So we'll start with 525 grams of sodium dioxide. And I'm just going to write my units first, okay? So you can kind of refresh your memory on how to set up stoichiometry. So grams of Na2O2 and then moles of also Na2O2. How about I let you finish that off? I'll wait 10 seconds. My next step is mole ratio, and the mole ratio is from moles of Na2O2 to moles of carbon dioxide. Okay, so here 1 mole of sodium dioxide is 77.98 grams. I calculated that already. And the mole ratio here is 2:2. Even though it's the same, you should write it out, okay, just so that you know you've taken care of it. And this gives us 6.73 moles of carbon dioxide. So now we have to get the moles of carbon dioxide to liters of carbon dioxide, and the only way we can do that is by gas laws, okay, by PV is equal to nRT. So,
674.
what am I calculating for? Volume. So volume then is equal to nRT over P. But I'm going to tell you a shortcut. Ready? So you can do the V is equal to nRT over P without any issues. Okay, that's not a problem at all. If you forgot everything that we did in class today, you're most welcome to go ahead and do this. Okay, that's fine. You will still get the right answer. However, the shortcut is that you're dealing with STP conditions, right? At STP, 1 mole of gas occupies 22. I don't know how many times we're going to say this today. Okay, so 22.4 liters of gas. And we have 6.73, right? That's all we have. So in STP, this becomes an easy calculation, 6.73 moles of CO2, and 1 mole of CO2 will occupy 22.4 liters of gas. So whether you do it this way or you do it this way, they're both going to give you the same answer. You can try it out if you want to, but otherwise, trust me, which I think you do for the most part. Questions? No? We're good? Okay. Yeah. We'll find in the exam how good of a job I did. All right. Next question. Calculate the amount of sodium azide needed to produce enough gas for a 125 liters of airbag at pressure 1 atmosphere and temperature 25 degrees Celsius. Sodium azide, again, you've never heard of this. It is NaN3. And this gives us sodium and nitrogen gas. So NaN3, sodium azide is a solid, sodium is a solid, and then nitrogen is the gas. Balance the equation, and we have 2, 2, 3. All good. Just a little bit of a GK for you, general knowledge for you. Sodium azide is the compound that is used for airbags. Okay, and so in airbags, you don't want to use a gas that is explosive or combustible. Okay, and so nitrogen is a very, Juan is laughing. Of course you don't. Okay, and so nitrogen is a really good gas. Okay, for that reason. You don't want to use carbon dioxide also, because if you inhale too much carbon dioxide, you can get poisoning from that. Oxygen, definitely not a good idea in a car accident. Okay, and so you want to use a gas that is relatively non-toxic and also easy to make. So this is easy to make. However, sodium azide itself as a compound is very dangerous, okay, in a way, which is why it explodes, right, on impact. If it was not explosive, then it would not explode, okay, like this on impact. So it's a very dangerous compound. You have to be really careful working with it. We work with it in the labs also, but it's really, you have to be careful, okay, because it is an explosive. So this is the reaction it gives, okay. So if you have sodium azide, okay, and then it will give you sodium and nitrogen. Now sodium is a metal over here, correct? It's not an ion, it's not a salt, okay, by any means. It's a sodium metal. Anyone seen sodium metal? Okay, so for those of you who are in my lab, you might get to see it. Okay, for one of the labs, I will show it to you. But sodium is an interesting metal, and we talked about the fact that you don't find sodium in nature, right? Because it's very reactive. So you don't find it in nature. Remember that question in your, was it in the pre-lab or was it the post-lab? I think the copper post-lab, right? They were asking you, why don't you use potassium and sodium? I got all sorts of interesting answers in there. Okay, it doesn't have the same charge, you know, it doesn't react as much as magnesium. Really? I thought we talked about this, okay, and the fact that you do have an activity series in your textbooks, okay, which shows you that sodium and potassium are way up there, okay, in activity. So they react very fast. So the amount of sodium that you would produce over here would be very little, because if it was a lot, that would also be a dangerous point, okay, to work with. So this is a small amount that's actually made here. Okay, so then let's get back to our question over here. We need to have 125 milliliters of nitrogen. So the question is, how much of sodium azide do we need? Okay, I want you to see the difference between the two problems, okay, that we're working. So this problem that we started with, we were starting with grams, correct? We were starting with grams, we were calculating volume. Here we are given volume and we are calculating grams, okay? Those are the only two combinations, permutations possible, okay, for these kind of questions. You'll either be given grams or you'll be given volume, okay, that's it, okay, that's about it. So over here, we'll start with PV is equal to nRT. So there's only one way you can do it, okay, either you do the stoichiometry first or you do the gas law first, okay, so depending on what kind of question you have and what data is given to you, you decide. Okay, whether you want to do stoichiometry first or gas law first. Since the volume is given and you need moles, okay, so then it means you need to find moles first, okay, using the gas laws. So here N is equal to PV over RT, okay, and so then pressure is given us as 1 atmosphere, volume is of course the 125. Liters, temperature is 27, excuse me, it was 25 actually. I wrote 27. Did you write 27? Mm-hmm. Did everybody did? Okay. Can I change that to 25 please, if you don't mind? 298 total. Let's do this.
Oh, never mind.
25, 273, so 298 Kelvin. Okay. R 0.0821, and then temperature is 298. Otherwise, I'll have to do my calculation again. Okay. And this gives us 5.109, and this is moles. Once you have the mole, what is my next step now? This is moles of nitrogen. This is moles of nitrogen that you just calculated. So what do I do next? Mole ratio. And the mole ratio will be to sodium azide. Okay, because that's what I'm calculating for. Very good. So moles of nitrogen down here, moles of sodium azide. And then convert sodium azide to grams. So 3, 2, and 65.02 is the weight of sodium azide, and the answer is then 222 grams. Yes,
How do you determine that we found out the mole of the nitrogen?
because that's the only thing that was given to us.
Oh, okay, yeah.
Yeah. If there were 2 or 3 gases in there, then yes, okay, you have to watch out for that. But in this case, there was at least only 1 gas given to us. So which means we need 222 grams of sodium azide so that we can get 125 liters of gas. But that liters of gas that we're talking about is only at 1 atmosphere and 25 degrees Celsius, okay? Because remember, gases are very sensitive. Good so far? Okay. These are the 2 permutation combinations possible for stoichiometry. However, we have the gas over water thing too, okay, to talk about. So here is another problem. And this is slightly different from what I have before, just so that you have something different, okay, to look at. Okay, calculate the mass of oxygen produced by decomposition of potassium chlorate, KClO3, when 821 liters of oxygen is collected over water at 30.0 degrees Celsius and 1.015 atmosphere. So I'll write the equation. KClO3 to give oxygen. And what's my other product? What do you think? Potassium chloride. Very good. And so we balance the equation as usual. So we have 3 here, 2 here, and 2 here. Solid, gas, solid. So here is our data. Okay, here is our data. Calculate the mass of oxygen produced. Calculate the mass of oxygen produced when 821 liters of oxygen is produced. So, which means that this is not exactly stoichiometry problem. Do you see that? Yes? Okay. Because I'm not asking you for how much potassium chlorate is required, okay, to give this much of oxygen. I'm just asking you to convert the liters to grams. Okay, that's all we're doing. So read the problem carefully and don't make it complicated for yourself. Okay, so there is no stoichiometry involved here, which means there is no mole ratios, okay, involved over here. This is just converting liters into grams. But we do have gas over water, okay, so this is collected over water, so we need to just have that little calculation there, okay? So we'll have to find the pressure of water at 30.0 degree Celsius. Okay, that's what we'll have to do. So wherever you see that collected over water, automatically you should be looking for a table, okay, to find the pressure of water. And so this is 31.8 mmHg from the table that I used. And so therefore you can convert either this to atmosphere, or you can convert the other atmosphere into millimeters of Hg, whichever you want. And honestly, we're going towards the gas law, so we might as well just convert this to atmosphere. Okay, it might be easier. So 31.8 divided by 760. Okay, and that gives us 0.0418 atmosphere. So P, oxygen then, the pressure that is given to us, that's the total pressure. Okay, so P 1.015 atmosphere minus 0.0418 atmosphere. So which means the pressure of oxygen is going to be 0.973 atmosphere. I want you to note one thing over here as you're writing this down also, is look at the numbers. The pressure, the total pressure is 1.015 and the pressure of oxygen is 0.973, which means the change was only 0.0418, right? That's what we just subtracted. Is that a huge number? It's a very small number, okay? Which means that when you do your calculations, sometimes you don't even realize you did not do the subtraction, because your answer will still come out to be approximately the same, okay? And so you'll be like, oh, it's only 0.02 different from what my answer is supposed to be. I'm sure this is the right answer. So usually for these kind of problems, you just have to watch out a little bit, okay? Because that little 0.02 difference in your answer will matter, okay? Because of the pressure of water, okay, in there. So when I give you problems like this, I am looking for this, okay, in there. So your answer, your method is going to be correct, except that you missed out this part, okay, in there. So you just have to remember, okay, to do this little calculation here. So now that we have the pressure, we can go ahead and use PV is equal to nRT now. Okay, so PV is equal to nRT. What are we calculating for? We're calculating the N over here, okay, moles, yes.
Can you also use P1, V1?
You can't use P1, V1 here because you're not looking at different conditions.
Okay.
Yeah? If you were looking at a different set of pressure, different set of temperature, then you would use that.
Okay.
Okay. So here we only have to use ideal gas law. You are calculating moles here because that's the only thing you can calculate from here, and this is the only way you can convert liters to grams. So once you calculate the moles, you will then convert the moles to grams. Okay, that's how you will do the conversion. So then N is equal to PV over RT. So pressure now is this new one. Okay, so 0.973 atmosphere. The volume is 0.821 liters. Please make sure you convert. And I wrote liters, didn't I? Okay, this was, I'm making all sorts of mistakes today. This was supposed to be milliliters. Here, we'll just add the M there. Okay, my bad, I'm very sorry. Okay, so convert the 821 to milliliters if you can. Please go back. Otherwise you'll wonder what happened. I'm sorry. 821 milliliters, 821 milliliters, so this is 0.821 liters then. Did you get it all? Okay, all right, I'm sorry. Okay, so it'll be given to you in the exam, or you remember it?
Oh,
Okay.
It will be given to us?
Yeah, but by the time you do so many problems, you will remember this. Yeah.
I already remember.
Yeah, exactly.
I'm
So
already like natural.
by the time you do 5 problems, there's no way you can't remember the gas constant. Okay, but it's a constant which is always given to you. Okay.